Hello. In today's session, I am going to talk about phase transfer catalysis. All of you know about the importance of catalysis in industry. This is an additional method which is very important in carrying out reactions even on industrial scale. My lecture plan goes like this. I'll introduce you to the subject of phase transfer catalysis. What is the role of PTC, that is phase transfer catalysis? The most quoted reaction, that is cyanide displacement reaction, in order to know what exactly is PTC. Probable reaction pathway, crown ethers as PTC, then some discussion about mechanism of phase transfer catalysis, in which I will talk about Stark's extraction method, Makozza interfacial mechanism, types of phase transfer catalysts, industrial process as an example, and the main advantages of phase transfer catalysis. We know that for a reaction to take place, the reacting molecules must collide with each other. They must collide with each other with sufficient energy to get the desired rate. For a gas phase reaction, it is not a problem. But in the reactions involving liquids, if the reacting liquids are immiscible or the reacting solid is not soluble, it will be a challenge to bring them together in sufficient concentration to attain desired rate. The commonly used method in the laboratory to overcome this problem is to use a solvent which can dissolve both the reagents. In many applications, however, use of solvents is not desirable. For example, in the synthesis of drug molecules or molecules with food applications, it may prove to be uneconomical on an industrial scale too. Therefore, we have to think of an alternative method, and here comes the role of phase transfer catalysis. Phase transfer catalysis offers a solution to overcome all these problems we thought of when we carry out reactions in which the reactants are not miscible. PTC refers to reaction between two substances located in different immiscible places or phases in the presence of special type of catalyst. Avoidance of solvent is not the only or principal advantage of this method. The main function of PTC in two-phase reactions is that a suitable phase transfer agent, when used in catalytic amount, can bring one of the reactants into the normal phase of the other reactant in such a form that high reaction rates can be obtained. That means there are two things a phase transfer catalyst does. The one, transfer the reactant into the other phase and activate it so that the rate increase takes place. That means role is two-way, transfer and activation. That means a phase transfer catalyst does what it says. The most quoted example to highlight the importance of PTC is the reaction which have historically required the use of sodium alkoxide as a base. PTC based method that avoids the use of sodium alkoxide gives as good or better results using a two-phase system with aqueous sodium hydroxide. The most common example is cyanide displacement reaction, by an alkyl chloride or bromide. You can see the reaction here. We have the alkyl chloride, sodium cyanide, which gives the product, and NaCl is the waste product. It is observed that simply heating and stirring two-phase mixture of 1-chlorooctane, the alkyl halide we are talking about here, with aqueous sodium cyanide leads to essentially zero yield of 1-cyanooctane even after several days of reaction time. On addition of a small amount of an appropriate quaternary ammonium salt to the reaction system, considerable increase in the formation of 1-cyanooctane is observed in essentially 100% yield in just 1 or 2 hours. We can see here not only the rate is increased, the reaction time is also very less. The general outline of the catalytic sequence we can try to understand here. You can see the equilibrium that is established here. The quaternary cation, that is Q plus, selected for its high compatibility of organic phase, transferred cyanide ion into the organic phase, and this is done as Q plus Cn minus, that means an ion pair which then undergoes reaction with chlorooctane to produce cyanooctane. Q plus Cl minus formed during the reaction is rapidly reconverted to Q plus Cn minus either in aqueous phase or at the organic aqueous interface by anion reaction with NaCN from aqueous phase. Use of hexadecyl tributyl phosphonium bromide as a PTC or phase transfer catalyst in this reaction increases the rate 1000-fold at 105 degrees centigrade with 94% yield in about 1.8 hours. Significant reactivity enhancement takes place due to the generation of quaternary phosphonium cyanide, which makes cyanide anion organic soluble and sufficiently nucleophilic. Thus, PTC brings about both anion transfer from aqueous phase to organic phase and activation is brought about. In the absence of hexadecyl tributyl phosphonium bromide, no reaction occurs. The advantage of using PTC is very clear with this example. In the case of two-phase reactions involving salts, crown ethers can also act as PTC, like dialkyl polyethylene oxides, which form reversible complexes with many cations. You can see here the same reaction or similar reaction where KCN is used instead of NaCN, and we use 18 crown 6 as the catalyst. We can see the product formed and KCl as the byproduct. The crown ether actually transfers the entire KCN molecule into the organic phase by complexation with K plus. Let us now look at some examples of phase transfer catalysts. Tetraalkyl ammonium or phosphonium salts are extensively used, out of which tetra-N-butyl ammonium bromide, methyl triethyl ammonium chloride, hexadecyl tributyl phosphonium bromide are important. Triethyl benzyl ammonium chloride and the crown ether that we just talked about is also useful. This is the structure of tetra-N-butyl ammonium halide. Mechanism of PTC. Mechanistic aspects of phase transfer catalysis are yet to be fully understood. Why? This is mainly due to difficulty in investigating biphasic systems, in analysis of many complex parameters, However, two pathways have been proposed. One, Stark's extraction mechanism. Two, Makosza interfacial mechanism. Stark's extraction mechanism. As per this mechanism, phase transfer catalyst moves back and forth across the organic and aqueous phases. The onium salt that is formed, that is Q plus X minus, equilibrates with the inorganic base MOH, you can see here, in aqueous phase and extracts hydroxide ion into organic phase. Onium hydroxide ion then abstracts hydrogen from acidic organic compound to give the reactive intermediate Q plus R minus. The other mechanism is Makosza interfacial mechanism. As per this mechanism, there is initial formation of metal carbanion at the interphase. You can see at the interphase carbanion is formed. This is followed by extraction of metal carbanion species from the interphase into the organic phase by the action of PTC. This mechanism is more likely to be applicable to systems where phase transfer catalysts are highly lipophilic and are reluctant to enter the aqueous phase. Types of phase transfer catalysis. The phase transfer catalytic processes can be classified as follows depending on the number of phases involved and also on the type of phases involved. The first one is the one that we discussed, liquid-liquid phase transfer catalysis. The second one is solid-liquid phase transfer catalysis, and the third is the third liquid phase transfer catalysis, where you have a third liquid that is participating in this case. Liquid-liquid phase transfer catalysis mechanism has been discussed earlier and it is the most popular mechanism. Solid liquid PTC. The solid liquid PTC has also been used for conducting a wide variety of organic transformations. The solid liquid PTC usually involves reaction of an anionic reagent in solid phase with a reactant located in contiguous liquid organic phase. Third, liquid phase transfer catalysis. This is an observation made by Newman and Sasson in 1984, who investigated the isomerization of allyl anisole using polyethylene glycol as catalyst in toluene and aqueous KOH solution, and observed a third liquid phase formed between the aqueous and organic phases. Let us look at a traditional process, cyanation of alkyl chloride, just to compare it with a PTC based process. Cyanation of alkyl chlorides is a major way to produce nitriles. In industrial process, since RCl and NaCN are mutually immiscible, solvents that are lower alcohols and water mixtures are used for the reaction to proceed. In this process, product has to be separated from the solvent and the solvent is reused. That means we are using a solvent, that itself is a disadvantage. Another disadvantage is that the wastes produced in substantial quantities have to be destroyed and disposed. We can compare that with the industrial process that is using PTC methodology. In this PTC methodology, neat alkyl chloride containing 1% molar catalyst is stirred with a saturated solution of sodium cyanide in water. On completion of the reaction in the organic phase, we get the product in pure form, which is separated. Product is subsequently purified if necessary or can be used as such. After separation of solid sodium chloride from the aqueous phase, it can be reused by introduction of fresh sodium cyanide. Only waste in this method is sodium chloride. Let us now look at some other industrial processes. Several other reactions such as addition reaction, reduction reaction, oxidation reaction with the participation of inorganic anions can be carried out efficiently by using this methodology. What are the advantages of PTC? 1. Elimination of harmful organic solvents. 2. Elimination of dangerous, inconvenient and expensive reactants. High reactivity and selectivity of the active species. High yields and purity of the products. Mild reaction conditions. The procedure. Low energy consumption. Low investment cost, because it is important if the process is to be used on an industrial scale. Minimization of industrial waste, again from economic considerations this is very useful. Let me now summarize what we have discussed about phase transfer catalysis in this session. I introduced this term to you, phase transfer catalysis. About catalysis you know, but phase transfer catalysis has a unique place in catalysis science. Role of PTC, how actually it is able to bring about the reaction. And as an example, we discussed cyanide displacement reaction. We also talked about probable reaction pathway. How crown ethers can act as PTC, we have seen as an example. The probable mechanisms of PTC, in which we talked about Stark's extraction mechanism and Makautsa interfacial mechanism, and types of phase transfer catalysts, industrial processes and advantages of PTC.